I want to do a couple of application problems involving vectors. And before I do, I want to make sure that we just understand that if a unit vector, if a unit vector is simply its vector, a vector, divided by its magnitude, right? And I'm just going to do this just kind of rec recognize that we're dividing here by its magnitude, then multiplying both sides by its magnitude, then it makes sense that any vector is simply a unit vector times its magnitude, right? The magnitude here. So we can say that any vector is simply the magnitude times its unit vector. And a unit vector can be expressed in a number of different ways, but again, we can also express a unit vector trigonometrically, simply meaning that the cosine of some angle theta represents our x component, and the sine of some angle or our direction angle would represent our y component here. So that's all I'm mentioning here. I'm expressing it in a number of different ways, including using linear combinations for our unit vectors, but we're going to leverage that bit of information as we go into some of these application problems. All right, so let's take a problem where we're dealing with a bearing. So we've got an airplane that is traveling at a velocity of 724 kilometers per hour at a bearing of 330 degrees. So if the wind velocity is 32 kilometers per hour in the direction of north 45 degrees to east, we want to find the resultant speed, which is the magnitude, and the direction, which is the bearing of the plane. So one of the key ideas here that we want to make sure that we understand is that the magnitude of a vector is going to give us its speed in this case. So let's start by drawing our vector diagram. So I'm just going to go ahead and set up my vertical line just to indicate that I'm going north. See if I can do that a little bit better. There we go. And then draw my horizontal line just to express my east and west. So we've got an airplane and it's traveling 724 kilometers per hour at a bearing of 330 degrees. Well, let's think about what that looks like. If we are traveling 330 degrees, or our bearing is 330 degrees, that means this airplane is going to have, I'm just kind of over exaggerating this here, but if this angle is 30 degrees, then that means this entire bearing here is 330 degrees. So 330 degrees. So here's my vector. I'm going to draw the arrow at the end to indicate that this is my vector. And I'm just going to label this vector here P, just for my plane vector. So there's a vector that is the vector that represents the plane's speed and direction, its magnitude and its direction. It's got its bearing and its speed, magnitude. So we see that the magnitude of our vector P, is 724 kilometers per hour. So the magnitude of vector P is equal to 724 kilometers per hour. That's its speed. All right. Now it then tells us that the wind velocity is 32 kilometers per hour in the direction of north 35 degrees due east. So let me switch colors here just to indicate now I'm going to be drawing the vector for the wind. So now I'm going to be expressing the wind vector. And I'm going to draw this here. I'm going to kind of use this to recalibrate. So which way is the wind blowing? It's from the north. It's going to be blowing 35 degrees due east, meaning from the north, it opens 35 degrees towards the east direction. And so this here would be my wind vector. Okay, and I'm going to label that as my wind vector. Okay, so there's my wind vector, and the magnitude of my wind vector is 32 kilometers per hour. So what's happening here? We have a plane that is traveling at a bearing of 330 degrees, right? Which, because it's an air navigation problem, we have a bearing that starts from the vertical, opens all the way around 330 degrees. And we've got a wind vector, or the wind that is blowing against the plane at a bearing of north 35 degrees to east. And so what that wind does is it pushes the plane off its course. What we are tasked with finding then is the resultant speed and the bearing of the plane. So this is the actual bearing, or I should say the actual vector that the plane is traveling with the wind taken into account. Because the wind is pushing that plane off course a bit, what we want to find, this resultant vector here, we're just going to call P plus W, What we want to find here is that plane's speed. What is the magnitude now of this plane? And what is the bearing of this plane? Well, so let's start by doing a couple things. Let's write the vectors. Let's express the vectors first for both P and W. So vector P, to start off, we say is its magnitude times its unit vector. Its magnitude was 724 times its unit vector, which was the cosine of, now let's think about what this angle is here before we just go ahead and say 330 degrees. The cosine of, well, we know that when we're expressing angles trigonometrically, we want to write the angle from the positive x-axis. So from the positive x-axis going towards this. So this is the actual angle that we want to describe. Well, what would that angle be? We know it's 90 degrees plus 30 degrees. So we would say cosine of 120 degrees. And then we would then say sine of also 120 degrees. If we express that, we would then evaluate those trig functions. So it's 724 times cosine of 120 is negative 1/2. Sine of 120 is root 3 over 2. And so this would give us negative, let's do some math here, 362. And then 362 root 3. So there's our P vector here, or our vector for our plane. Now let's go ahead and let's do the wind vector. Let me make this a little bit smaller here. So now let's do the wind vector, and the wind was in blue, so I'm just going to do this in blue. So for our wind vector, its magnitude was 32 kilometers per hour times what is the angle for our wind vector? Well, here we said it was 35 degrees. You know what? I'm going to change that value just because I want to keep this problem as one that we could potentially do most of it without using a calculator. So let's change 35 degrees. Let me just change that. Let's change that to 45 degrees. Let's go to 45 degrees. So again, I'm going to change that over here. 45 degrees. That way it's a nice angle that we're used to working with. So we're going to say that that angle for the wind vector was cosine of 45, sine of 45 degrees. Okay, so this wind vector here, we're then going to say is 32 times root 2 over 2, root 2 over 2 is equal to 16 root 2 times 16 root 2. Okay, so now that we have this, our resultant vector P plus W is simply the sum of these two vectors. And in our previous lesson, we talked about how to add vectors. So we're going to add our horizontal components. We're going to add our horizontal components. So we're going to say this vector is negative 362 plus 16 root 2. That was our horizontal component. And then we are going to add our vertical components, or our y components there. So we're going to say that is 362 root 3 plus 16 root 2. And these are our vertical components. So there's our vector, but the problem is asking for the magnitude of this vector and its bearing. So we're going to need to first find its magnitude. So let's find the magnitude of P plus W, which again is just a distance formula. So this looks a little gnarly, but bear with me. Bear with me. See what we did there? Okay. All right, plus 362 root 3, our vertical component, squared. Send that out. And this we are going to need a calculator for. And let me actually punch that into my calculator real quick. We should get approximately 732.934 kilometers per hour. This is our speed. This is our speed. So the magnitude of this vector is its speed of the plane. Now we want to finish this up by finding the bearing of our plane. So let's find the bearing. So the bearing of the plane is going to be our direction angle. So what we need to find is, just to kind of go back here, actually I'll keep this in purple. What we need to find is this actual angle here, from the positive x-axis to that. Well, let's think about how we can use the components of our vector here to actually determine this angle. So we know that if we do theta is equal to the arctangent of y over x, or our vertical component of our vector. So what was our vertical component? It was what we have highlighted in green. So 362 root 3 plus 16 root 2 all over our horizontal component, which is what I underlined in red above for our p plus w vector. That's negative 362 plus 16 root 2. And once we put that into the calculator, and pause and think about that, but we should get theta is approximately negative 62.417 degrees. Now let's pause and think about this. Remember, our calculator is calculating with the range of inverse tangent in mind. And because it's doing the inverse tangent of a negative argument, it's giving me an angle between 0 and negative 90 degrees. But what we want to do is use that angle to figure out what this bearing is. So what did the calculator actually give us? Well, if we go back to our diagram here, the absolute value of this angle, negative 62, is actually describing, and I'm going to just do this in this color just so we can see. The calculator actually gave us this angle here. This is 62.417 degrees, 62.417 degrees. Well, if we find the complement of that angle, then we'll get this. We'll then get this angle here. And once we know that angle, which let me just actually punch this out right now. Let's go ahead and do this. That's right. Theta, this angle alpha is equal to 90 minus 62.417 degrees. And that's approximately 27.583. Okay, so 27.583 degrees, that represents this angle up here, this angle up here. So how do we use that to find its bearing? Well, I know this diagram is getting a little unwieldy at this point, but what we want to think about then is, since this is an airplane bearing, we want to say that the bearing is going to be this entire angle from the vertical line going all the way around until we hit this bearing. So in other words, it's simply 360 degrees minus this angle alpha. So we can say the bearing actually is 360 degrees minus alpha, this angle here. And so the bearing of PW, or P plus W, I should say, is approximately 332.417 degrees. So I know that got a little gnarly just with all the angles that we had to keep track of here. But if we think about, again, what we are trying to find, and you make sure we understand what the inverse tangent is actually giving us, then we can see how we get that angle alpha, and then use that to find the bearing from the vertical line all the way to where P plus W, our resultant vector, is.